this is the 11th lecture in the series. Till now, what we had looked at was developing the finite element method to solve a typical one-dimensional problem. And the typical one-dimensional problem that we had taken was an axial bar subjected to some end load P and a distributed axial force F. The bar is of length L. And we had said that the bar could be constrained at the end x equal to 0, and it could also have a uniformly distributed axial spring, that is, it is lying on an elastic support which is going to apply a constraint to the motion or give a resistance to the motion. So, and or. So, for this problem we had developed the finite element method, where our approach was to make a mesh, and for this we had made a uniform mesh. And take approximations of order P. P could be 1, 2, 3, anything, and this was uniform approximation, that is, all elements had the same P order of approximation. And what we had done is we had highlighted the fact that the solution, the finite element solution, is given as ui, summation of ui phi I x, where this n is number of elements. And P is the uniform order of approximation. So, this is what we had done. Then we had said that these phi i's could be constructed by piecing together element shape functions. Shape functions how had we defined these element shape functions? That if this is the generic element k, so I will have this as the first point, the first node, or the left hand vertex or the edge of the element as the node x1k for the element. The right hand vertex is node xp plus 1k of the element, and in between we have uniformly spaced p minus 1 points. So, this will be point x2k and this will be point xpk. This is how we had defined the element, and over the element we had then gone ahead and defined the shape functions, which were like this. So this would have been our n1k. So, given a generic element, we were able to define the shape functions of order p at the element level, and we said that the global basis functions are obtained by piecing them up. And here we had seen the definition of the so called edge functions and then the internal bubble functions and so on. Now, what are the problems with this? Problems with using this kind of an approach. There are really no problems, but the basic difficulty that we are going to face is the following, that the shape functions, as p increases, shape functions become more complex higher order polynomials. And so does their derivatives. So when I have to evaluate what we had done, after this we went ahead and evaluated the stiffness entries at the element level. So this we had done like this. You could have EA of x k dx dnj k dx. So when we evaluate this integral to obtain the entries of the stiffness matrix, we find that this expression, the integrand, the expression dni dx, dnj dx, even EA need not be constant all the time. EA could be anything. It could be coming out of this kind of a profile, or it could be coming out of this kind of a profile, anything. So EA also has a complicated expression, may have, for the problem of interest. So in all these cases, to obtain each entry of the stiffness matrix, we have to do this integration manually. Now this integration may not be so easy to do. By hand we can do it, but it will take some time. Also, this integration cannot be automated. Which means that we cannot convert the procedure that we had followed till now to obtain the stiffness matrix entries, that cannot be converted into a computer program, because the computer is not capable of doing these integrations in such a nice symbolic way as we can do. So that is one problem. Other thing is that if you take the load vector entries, you see that here the load vector has this distributed force term. This could be anything. It could be a cosine kind of a load, it could be a sine kind of a load, it could be a polynomial load, it could be unsmooth, it could be anything. Now in each of these cases, if I have to use the finite element method to get a solution, I have to do these integrations specifically for the kind of load which is applied on the member. Now this job will become very cumbersome. We do not want to have to do this job over and over again, separately for different loadings, separately for different material constants, etc., for different order of approximation P. So we would like to bring it into a common platform which could be automated. So automation is something which we would like to aim for. That is, computer implementation becomes mandatory now. So how do we go about doing it? The idea is simple. So let us take a generic element ik such that the first node of it is x1k and the other one, the last node of the element, is xp plus 1k. This we will call our physical element, because this is the actual domain that is given to us. What we are going to do is, we are going to say that this physical element, this generic physical element, comes from something called a master element. That is, we are going to define an element like this, So this I can say is the point psi 1 psi p plus 1. This master element is again, if you see, an interval which is of size 2, and it always goes from the point -1 to +1. So this is called the master element. And every point in the physical element, that is, you take any point here x, could be obtained from a corresponding point in the master element by a linear map. Linear map or an affine map. So we say that x is a function of psi, and this is linear. That is, it is given by a psi plus b. So given the point psi, I can find the point x. Now, how do I define this linear map? So this linear map, what does it do? If I go back, it takes the point x1k to the, that is the point psi 1 to the point x1k, the point psi p plus 1 to the point xp plus 1k. Now to define a linear, we have to give its value at 2 points. So we are going to give its value at the point psi 1 and psi p plus 1. So let's go back and say that we know that x1k is equal to a into psi 1 plus b, which is equal to minus a plus b. Similarly, the point xp plus 1k is equal to a psi p plus 1 plus b, this is equal to a plus b. So from here I would like to find out what is a and what is b. So b, if you see, will come out by simply adding up these two things as half of xp plus 1k plus x1 of k, and a will come out to be, if I go back and put it in there, as x p plus 1k minus x1 of k. Okay. So in this case, we can define now xi. I'll put the a and b in the expressions, and I'll collect terms, and I'm writing the final expression. It is going to be x1k into half of 1 minus psi plus x2 of k into half of 1 plus psi. So this is now the mapping by which any point psi, when it is given to us in the master element, we can find the corresponding point x in the physical element. Okay. Now, since this is a linear map, it also implies that a polynomial of order q in the physical element remains a polynomial of order q in the master element, because the mapping is linear. Remember that it's a linear map, that's why this is true. So if I have my shape functions defined in the physical element as we had done earlier, ni, which is a polynomial of order p. This will, by employing this mapping, it should map to a polynomial of order p in the master domain. So this is order p, this is of order p also. Okay. So the shape function, if I transform it using this mapping from the physical to the master element, it remains a polynomial of the same order. Further, what do we know? That the shape function, if it had a particular value at a given physical point xi, it also will have the same value at the given master point psi I. So we will say that the polynomial ni at the point we had given these points x l of element k will be equal to ni hat at the point at the master point psi l, where xlk is now obtained by the suitable linear map from the point psi l. Okay. So for example, if I had a quadratic element, so this was my x1 of k, this is going to be my x2 of k, this is going to be my x3 of k, and in the master domain the corresponding point will be psi 1, psi 2, psi 3. Now we know the way we had defined things earlier, that this point x1 of k is at the midpoint of the element. So if I do the mapping, this point psi 2 will be at the location 0, which is the midpoint of the master element. And if I had defined a function, the shape function in the physical domain, let's say the first shape function like this, which had a value 1 at the point x1 of k, and 0 at the points x2 of k and x3 of k, then in the master domain it will have the same feature, that this value at the point psi 1 will be equal to 1, at the point psi 2 and the point psi 3 the value is going to be 0. So now, since this n1 hat is a polynomial of the same order as n1k and so on, can we define these shape functions in the master element? So shape functions defined in the master element. So first let us look at the linears. How do we define the linears? So when linears correspond to p equal to 1, so here we had the physical element, and this was my n1 of k, this was my n2 of k, this was my point x1 of k, this is the point x2 of k. Similarly, this is my master element, this is the point psi 1, this is the point psi 2, and This is the function n1 hat, this is the function n2 hat. Can we now give what is this function n1 hat as a function of psi? What is it equal to? It is very easy. We will follow the same principle that we followed in the physical element, that is, we will use the definition of the Lagrange polynomials that we had given in the physical element. Now that definition will be applied to the master element. So here obviously what we are going to say is that it is a linear which has to vanish at the point psi 2, and it should have a value 1 at the point psi 1. So psi 1 minus psi 2. Now what is psi 1 minus psi 2? It is going to be equal to minus of 2. So this is going to be minus 2, and psi minus psi 2, what is psi 2? 1. So it is going to be equal to minus of half into psi minus 1. So this is going to be equal to half of 1 minus psi. So this is the definition of the first shape function, the linear shape function, first linear shape function. Similarly, n2 hat of psi is equal to, so it is psi, it is a linear which vanishes at the point psi 1, psi minus psi 1, and it has a value 1 at the point psi 2. Now psi 1 for us is equal to minus 1, and this is equal to 2, so it becomes half of 1 plus psi. So the second shape function and the first shape function can be defined using exactly the definition of the Lagrange polynomials, but applied to the master element. And remember that here the values have to vanish at points which are appropriately obtained by mapping from the physical element. Okay. So similarly, if I want to go to p equal to 2, for p equal to 2, how are we going to define this shape function in the physical element? Now I am not going to do it in the master element, in the physical element, I will do it in the master element. So here is my psi 1 which is equal to minus 1, here is my psi 2 which is equal to 0, and here is my psi 3 which is equal to 1. Now the first shape function for the quadratic is going to be 1 at the point psi 1, 0 at the point psi 2, and the point psi 3. So this is going to be my n1 hat. Similarly, the second one is going to be 1 at the point psi 2 and 0 at points psi 1 and psi 3, and the third one is going to be 1 at the point psi 3, 0 at the point psi 1 and psi 2. So again we use the same definition of the Lagrange polynomials that we had defined earlier. So I know that my n1 hat as a function of psi will be equal to psi minus psi 2 which is 0 into psi minus psi 3, that is it has to vanish at the point psi 3 which is 1, and here we will have psi 1 minus psi 2, so minus 1 minus 0, here I will have psi 1 minus psi 3. So you see this will become equal to, this is minus 2, 2, so it becomes equal to half of psi into 1 minus psi, minus of half, minus half of psi into 1 minus psi. So this is what our definition of n1 hat for p equal to 2 will be. Similarly, I can define n2 hat. This has to vanish at the point n1 and n3, so it's psi minus this is going to be psi minus of minus 1, so psi plus 1 into psi minus 1, and it has to have the value 1 at the point psi 2, so 0 minus of minus 1 is 0 plus 1, 0 minus 1. So this is going to be equal to 1 minus psi squared. Similarly, the n3 hat psi will be equal to, if I go ahead and do the same job, it will be equal to psi minus 0 into psi plus 1 divided by 1 minus 0 into 1 plus 1. So this is going to be equal to half of psi into 1 plus psi. So the same job can be done now for the cubics. So for p equal to 3 also we can define the 4 cubic shape functions in the master element. Now the only thing is, one should remember that in the master element the points psi 1 is equal to minus 1, this is psi 2, this is psi 3, psi 4 is equal to plus 1. So we have the gap between these points is equal to 2 divided by 3. So this is minus 1, so this point becomes minus 1/3, this point becomes plus 1/3. So as we had given the algorithm earlier, we can apply the algorithm here, that the point, so for an element of order p, psi 1 is equal to minus 1 and psi 1 plus L is equal to psi 1 plus 2 by p into L. For L is equal to 1 to up to p. So what is this? Actually this 2 by p is nothing but the interval length between two consecutive points. So if I define these points psi k in such a way, then I can define my Lagrange polynomials which are nothing but the shape functions quite easily. So before defining the shape functions, we should define these points psi k and then go ahead and define the shape functions. So now if I have this definition of shape functions, how is it going to change things? So what we know is that we were interested in finding for a given physical element the derivative of the shape function with respect to x, because that is what went into our element calculation. So this will now become equal to this. That is, the derivative with respect to x will now be given in terms of derivative of the shape functions defined in the master element with respect to psi into the derivative of psi with respect to x. Now, if we go back to our definition of the element transformation, here if I apply the derivative, if I try to find the derivative of this with respect to psi, what will I get? I will get that dx from that expression that I had written earlier is equal to minus x1 of k by 2 plus x2k, sorry, not x2k, x p plus 1k by 2. So, this is into d psi. So, this is equal to, if I take this, what is xp plus 1 minus x1 for the element k? It is nothing but the size of the element k. So, I can write it as hk by 2 into d psi. So, dx becomes hk by 2 d psi. So, the derivative now can I substitute? So, d psi dx becomes equal to 2 by h of k. So, we will have dni k dx as a function of x is equal to dni hat d psi into 2 by hk. So, once I have done this transformation, then we have to also do the further transformations, that EA of x, because the material constants could be different, EA as a function of x is equivalent to EA hat x of psi. What does this mean? That now I can write, by using the transformation properly, that the function x, EA as a function of x can be written as a function of psi given by EA hat. Similarly, if I had the distributed springs k of x, that would be equivalent to k hat, which is a function of psi, and f of x, which is the distributed load, will be equivalent to f hat, which is a function of psi. So, this we can do and take all our material constants, the loading data, from the physical element to the master element. So, now let us use these transformations to now redefine the integrals over the master element. So, remember that we have done all this to bring the integrations from the physical element to the master element. So, now our earlier Kij for the element k was integral x1, I am going to drop the superscripts, or maybe I will add it, x1 to xp plus 1 k EA of x dni k dx dnj k dx. Now, this we are going to evaluate in the master domain. So, obviously when I transform, the transformation will take us from -1 to +1 instead of x1 of k to xp plus 1 k. So the integration domain will be from -1 to +1 all the time. EA will be replaced by EA hat, which is a function of psi. dni k dx will be replaced by dni hat d psi into d psi dx. And what is d psi dx? 2 by hk. dnj dx will be replaced by dnj hat d psi into d psi dx, which is 2 by hk, and dx will be replaced by dx d psi. I will explicitly put it dx d psi d psi. Now what is dx d psi? Dx d psi is called the Jacobian. Jacobian of the transformation. What is that physically? What does this Jacobian mean? It means the ratio of the length of the original element to the new element. So the ratio of the length, you see that if I go back to the expression that we had derived for the dx in terms of the d psi, this quantity will be equal to hk by 2, where if you see, this is the length of the master element and this is the length of the physical element. So ratio of the original element, length of the original element to the length of the current transformed element, that is called the Jacobian. So now if I club everything together, I will get that this Kijk is equal to, by doing the suitable cancellations, 2 by hk integral psi is equal to -1 to +1 EA hat ni derivative of ni hat with respect to psi, derivative of nj hat with respect to psi d psi. Now if I have the elastic support also present, then it is not difficult. In the case of elastic support, I will add this extra bit, integral psi is equal to -1 to 1, you will have k hat of psi into ni hat into nj hat. Now what do we have? Dx d psi will be hk by 2 d psi. So if I have the elastic support, this extra term also has to be added to the element stiffness matrix entry. Similarly, the load vector for the element will now look as integral psi is equal to -1 to 1 f hat of psi into ni hat d psi, and here I will have the effect of the Jacobian, which is hk by 2. The simple transformations, this we have all done in our calculus courses. So the advantage is now that from the integration over the physical domain, now we have brought all the integrals over the master domain. For any element, this is how we are going to do the integration. Okay. So once I have the entries of the element stiffness matrix and the element load vector, then I can go and follow the same procedure of assembly that we had followed earlier, then apply the boundary conditions. Nothing else changes. It's only in these integrations that we have come from the physical element now to the master element. Okay, so before we go ahead, let us pause and look at the motivation for doing this. The motivation, you remember, is that we want to go for a computer implementation, that is automation of this whole process of doing the element calculations, doing the assembly, applying the boundary conditions, and so on. So with that in mind, we had converted the integrals from the physical element to the master element. Now what I would like is that the following exercise should be done at this stage. Now that we are conversant with what a master element is, so I give the following inputs. The point in the master element, a particular point psi bar, I will call it psi bar. Okay, this is a point lying in the master element which I give, and I give the order of approximation p. Now p, let us take, is either 1 or 2 or 3. So 1, 2 or 3. Now given this input, what I want as output is the values of the shape functions ni hat at the point psi bar and the values of the derivatives of the shape functions at the point psi bar. So one has to write a program or a subroutine which will take the position psi bar in the master element and the order of approximation p as an input, and returns as an output dni, that is the value of the shape function in the master element and the value of the derivative of the shape function in the master element. Getting this expression out of this is a little cumbersome, but it is easily doable. So this should be done, and out of this the subroutine that comes now will be able to give us the values of the shape functions and their derivatives at any point in the master domain. Let me remind you that for a pth order element, the shape function by definition will be what we had done earlier, j equal to 1 to p plus 1 From this, finding the derivative is easy. But here we only want to do this exercise for p equal to 1, 2 or 3. Okay, so once we have this shape functions, so we have the shape function routine. What are the checks that one can do is that for the given psi bar, check whether the sum of all the shape functions is equal to 1 or not. Okay. The second check that we'll have to do, at least these checks can be done. This should be incorporated in the program, that sum of the derivatives of the shape functions at the point psi bar is equal to 0 or not. If it is not 0 and if this is not 1, then there is something wrong in the program, so one should go and check whether the program is doing what is wrong, where is the bug, and the bug has to be fixed. Okay. One should also take this program and output at suitably located points in this interval. So I can take smaller set of points, and at each of these points output the value of the shape function, each of the shape functions and their derivatives, and then plot it. So output value and derivative and plot it using a suitable plotting program, and see whether these functions are actually, they look the way we have been drawing them. That is, they have a value 1 at a particular point, the shape functions, and they vanish at the other psi i's. These things one should do before using this program. Okay. Once this is clear, then it will also give us a graphical image of how these shape functions look. Then what we are going to do is, this integral that we have defined over the, so I am calling a generic integrand this integral that we have defined, where g psi is a generic integrand, this will be now given in terms of a numerical integration. Numerical integration means we will replace this integral by a sum. Sum where? Sum over sum of the value of the integrand evaluated at certain points. So this is the topic of our next lecture, where we will talk of numerical integration and how to do it for the given integrands that we face in a finite element calculation. Thank you.